Today we're going to discuss an example of an implementation of the Markov chain Monte Carlo algorithm for fitting a location mixture of two Gaussian univariate Gaussian distributions. And we're going to test this algorithm in a simulated data set that's actually the same one that we use to test the EM algorithm for this same problem. So the first step is to generate our simulated data, and we use, as I said, the same setup we had used before. Two components in the truth. The weight of the first component is 0.6. The mean of the two components are 0 and 5. And the standard deviation, which is the same for both components, is 1. We're going to generate 120 observations, first by selecting what component each observation comes from randomly, and then generating from a normal distribution, where the mean of that normal is given by the component to which the observation belongs. And we can generate a simple plot that contains the density and the points that we just sampled. You have seen this graph before, so if you remember from the EM example, this is indeed a bimodal distribution, and you have clearly separated groups of observations that come from each one of the two components in the mixture. Okay, so that is the data that we're going to be working with. The first thing we need to do is we need to initialize the algorithm. In this case, the algorithm is initialized so that we assume that the weights are the same for both components in the initial state of the chain. And then the standard deviation of the components is assumed to be the standard deviation of the data. And the means of each one of the two components in the first state are just randomly sampled. And remember that initializing MCMC algorithms randomly is going to be important. So we initialize the algorithm randomly by sampling from normals centered at the mean, and assuming that the standard deviation of the mu's is essentially the same as the standard deviation of the data. And again, we can plot that initial guess of what the density looks like. And as you may remember again from the EM algorithm, that initial density looks a little bit like this, which at least covers kind of the right area for the data, but clearly doesn't show the kind of bimodality that we would have guessed that the distribution has. Okay, but that's just our initial guess. Now, the next thing that we do is we need to initialize the priors for the model. So we're going to be working, in this case, with a beta prior for W, and that means that the vector of parameters is just contains 1 and 1 in this case, and that just means that it's a uniform prior on omega. If you remember the prior that we assigned for the means of the components, it's going to be a Gaussian prior, and those are the two parameters. So the mean is going to be 0, and the standard deviation is going to be 5. And finally, the number of degrees of freedom for the prior on the variance is going to be 2, and the other parameter for the prior on the variance is going to be 1. If you remember, we had an inverse gamma prior here, so it's an inverse gamma with parameters 2 and 1. Okay, so we're going to do 6,000 iterations of the MCMC, of which we are eventually going to burn in 1,000, and we will monitor convergence of the algorithm using the log posterior of the model, and we will see that there is evidence that in that from looking at that quantity that 1,000 observations is probably plenty in terms of convergence. Okay, so the last thing that we need to do before the actual algorithm is to define variables where the output is going to be stored. So we have the cout variable that contains the indicators, and similarly variables that store the samples of the weights, samples of the means of the components, samples of the standard deviations, and this variable log post that contains the logarithm of the posterior over the different iterations. Okay, so the main MCMC sampler, it's located within this for loop here. And it has four big pieces. So the first piece is sampling the indicators. And if you look at this carefully, the code is going to look a lot like the code that you had in the E step of the EM algorithm. That shouldn't be surprising because you are computing the same posterior probabilities in both cases. Only that here you actually do sample the mixture components from those probabilities. And that's what we do in this line of code. Now, the other three pieces correspond to sampling the different groups of parameters. So first, the weight. In this case, because we started with a beta prior, we also have a beta posterior with just updated parameters. And this is what the posterior sampler looks like in this case. Similarly, for the means, we need to sample one for each component. And to do that, we need to, we know that because the prior is normal, the posterior is also going to be normal with updated parameters. And these are the two lines that compute those updated parameters based on the current assignment. And then you just sample for each component. And the final step has to do with sampling the variances. Again, because we started with an inverse gamma as the prior, we also have an inverse gamma as the posterior, and we just need to update the parameters, the number of degrees of freedom and the scale parameters. And then we just sample from an inverse gamma distribution to obtain the variance. And then to get the standard deviation, we take the square root of that quantity. Okay. So those are the four main steps. The rest of what's in the for loop just has to do with storing the values that we just sampled into the variables that we had defined in the beginning. And then we have a step that essentially just computes the normalized log posterior for the model. That's what this piece of code does. And again, we will be using this to monitor convergence. And finally, we just print out every 500 iterations what the current iteration number is. And that's just kind of a progress bar, if you will, to just let us know how far along the algorithm is at any given point. Okay, so let's run this code. It's not too slow in this case because we don't have that many observations or that many components. Now it's done. So we have done our 6,000 iterations. The first thing I want to do with those iterations is to plot the log posterior with the iteration number, again, to verify convergence. And you can see, so this corresponds to the initial steps of the algorithm when we our guess was not really good. And we can see that the log posterior was actually pretty low. It was down here. But in just a few iterations, it jumps up. And then it basically remains stable over time up here. So that suggests that the algorithm converges actually pretty quickly to where the mass of the posterior is. And you can see that probably 1,000 iterations is plenty in terms of ensuring convergence of our algorithm. So this is always reassuring when you see a plot like this. Okay, so now that we are more or less sure that we converge, the other thing that I want to do is I want to kind of do a plot of what the posterior distribution looks like. And let me first do it, and then I'll discuss a little bit what's in there. So we can see the black line here corresponds to the posterior mean of the density of the data. And the gray area corresponds to credible intervals, point-wise credible intervals for that density. Now, how did we get those? Well, what this code does is you first compute what is the form of the posterior distribution in each sample of your MCMC. After having discarded the burn-in period. So that's why you have this minus burn and this plus burning here. So this is just ignoring the first 1,000 iterations in this case for the sampler. And once you have essentially one curve like this for each sample of the MCMC, you can just do averages or quantiles for essentially each value of x in which you calculated the posterior. And that is what gets represented. So now what do we see here? So first of all, the posterior mean looks a lot like the true density of the data and actually matches what we would expect from looking at the data. So that's good. The other thing that we see is that there is actually very little uncertainty about how the density looks down here or down here. We have no observations there. So we're pretty sure that the density there should be close to 0. But we can see that close to this inflection points where you change curvature, that or where you go from increasing to decreasing, you can see that in this area is where most of the uncertainty is. So we're the most uncertain about, in some sense, how high the density is at the peaks. And that's, again, not surprising. That's something that we will observe pretty often when using Bayesian mixture models.